Yeah, next up is the chi-squared statistics, chi-squared test, whatever. What is that? Well, the statistics just takes two features and tells you how dependent those features are, or how independent they are actually. Yeah? Well, that sounds good, because if we take a feature and the class label, yeah, we could look at how dependent or independent this feature is from the class label. And obviously, the more dependent it is on the class label, the better, obviously. Yeah. So that is the basic idea of chi-squared, and we'll have a look at how that actually works. So here it is. The basic idea, once again, is to measure the independence of a feature from the class variable, and for that we look at the so-called contingency table, where we divide again the data based on a split value in this particular feature, or based on some discrete values. And we look at an example right away here. So we will have some observations, and the class attribute is actually playing chess or not playing chess. Yeah? And the predictor attribute, so the feature we look at, is the observation like science fiction or not like science fiction. So it's probably a categorical attribute, yes or no, or 1 or 0 or whatever. Yeah? And the contingency table just displays the distribution. So we have the observations that like science fiction, which are 450 observations like science fiction, and 250 of them play chess and 200 of them not play chess. Yeah? And then we have 1,050 observations that like science fiction, 50 of them play chess, 1,000 do not play chess. Yeah? And we have here all the summaries. So in summary, we have 1,500 observations. Yeah? And now the chi-squared test is actually very simple, because we look at all the different class values, yeah, all the different class labels, which are 2 in our case. Play chess is the first one, and not play chess is the second one. So the index I here in our case goes from 1 to 2, yeah, because we have 2 class labels. And then we also look at the different values in the predictor attribute, in the feature that we want to evaluate. In our case, again, these are only 2 values, so the J index goes from 1 to 2. The first value is like science fiction, and the second value for J is not like science fiction. And what we are doing actually is we take the observed values that are in this table here, and compute the difference to the expected frequency of value J in class I. So E here are the expected values, and we squared it and normalize it by the expected values. So what are the expected values actually? Well, we can look at the numbers here. So we know that we have 1,500 observations in total, and 4 or 5 of those 1,500 observations actually not play chess, and 1 of 5 of these 1,500 observations actually play chess. So that is the expected value. So we just have to look at how many of the observations like science fiction. 1/5 of those, that are 450, one out of 5 of these 450 that like science fiction are expected also to play chess, and 4 or 5 of them are expected to play chess. Yeah? And the same holds true for these 1,050 observations that not like science fiction. Yeah? So that is on the next slide here. The expected numbers are here in brackets. Yeah, one out of 5 of the 450 are expected to play chess. Yeah, so 90 of those guys here, of those observations, are expected to play chess. The other ones are expected to not play chess. And the same can be computed out of this number here, the total sum of the observations that do not like science fiction. We again expect 1 of 5 of those 1 years, which is 210, play chess, and 4 or 5 of those 1,050, which is 840, not play chess. Yeah? And now we can compute the chi-squared statistics, which is, well, 250 minus 90. This is the first one here. 50 minus 210. This is the second one here. 200 minus 360, and so on and so on and so on. And then we get some specific values. So how to interpret that? Well, the larger the values, sorry, that is a mistake here. The larger the values, obviously, the more we have a discrepancy between the observed values and the expected values. So the more independence, or the more independent the predictor attribute is. Yeah, the smaller the values, meaning that the observed values are more or less what we expect, meaning that the feature that we look at is actually dependent on the class attribute, then the smaller the value of the chi-squared will be. Yeah, so that is a mistake here. Here we look for smaller values. I will fix that in the final slides actually. Yeah, so the smaller the values here, the better, because the smaller means that the two things are more dependent on each other. So the feature depends, or the feature and the class attribute are dependent on each other, and that's what we want actually want. Yeah, we want features that can be used to predict the class attribute better. Those are the guys that are the features that depend on the class features, and not those that are independent of the class feature. Those features would have a large chi-squared value. Yeah, just yeah, I'll fix that, as I said before. Yeah, and last but not least, I want to show you mutual information, which is again a measure of how to evaluate a feature. Mutual information, as the name probably suggests, yeah, takes two features and it says, or it tells you how much, if you know the something about the first feature, how much do you already know also about the second feature. Yeah, so that is the idea of mutual information, and of course we also will have a look at that one here in the full length. So yeah, mutual information measures how much knowing about one of these values reduces the uncertainty about the other. Yeah, so in our case, it somehow measures how much information a feature contributes to making the correct classification. So how much, if I know something about the feature, how much do I know about the classification, yeah, the class label. Yeah, so yeah, the mutual information is based on probability distribution. So we look at different probability distributions. We look at them. So we look at, first of all, we compare two features, x and y. Y is, for example, the class label. X is the feature that we want to measure, the importance or the quality we want to measure. We take a look at these two probabilities, P of x and P of y, which are the marginal distributions of x and y, respectively, of course. Yeah, and then we also look at the joint probability distribution function of x and y. Yeah? And we relate those three things to each other as follows. Well, in the discrete case, we just have to sum up all these probabilities. Yeah? Especially we take the log of the joint probability divided by the marginal probabilities, yeah, times the joint probability. And in a continuous case, since we don't have these kind of histogram-based things, we need to take so we have, well, in the discrete case, you can think of having a lot of bins in a histogram. So we just sum up the height of the bins more or less, or not actually the heights of the bins, but somehow like that. And in the continuous case, we need to compute the integral actually, yeah, because we don't have the spinning anymore, but it's more or less the same actually. Yeah. So let's have a look at the discrete case, the same actually here. So if x and y are statistically independent, meaning that there is no correlation between them, so that is the worst case actually, yeah, then obviously, so if they are independent, then the joint probability can be computed by just multiplying the marginal distributions. Yeah, so that is the definition of statistically independence. Yeah, if two variables are independent, we can multiply their probabilities to get the joint probability. Yeah, so that is actually the definition of statistically independent. Yeah, so in that case, if this holds, then obviously this one here is this times the same, this divided by the same. So we have here 1 for this ratio, and then we get log of 1, which is 0, so the whole thing ends up in being 0. Yeah. So in other words, the smaller the mutual information is, the closer it is to 0. We don't know, so knowing X does not reveal anything about Y. So that is bad, actually. That is the worst case. Yeah? So we look for features that have a high information gain, or mutual information, sorry, a high mutual information in that case. Yeah? So that is another measure that can be applied for evaluating different features here. Yeah, a short roundup discussion for forward selection feature ranking. So the advantages is that it is extremely efficient because we just compare each feature separately to the class attribute, and then take the best K features according to these individual measures. Yeah, and if we won't do that individually, we would have to test all the possible k-dimensional projections, which would be n over k different subspaces. And if n is large and k is large, then this is pretty much, actually. Yeah. So in that case, it's just looking at each feature individually and then take the best k. And it works rather good for small sample sizes. Yeah? All those measures are okay in terms of stability, even for small sample sets. Yeah, the biggest limitation is obviously this independence assumption, which actually brings us a very, very good efficiency. But of course, classes and features must play a direct correlation in order to actually find good features. So in case of correlated features, it always selects the features having the strongest direct correlation to the class variable, even if there are features that are strongly correlated with each other. So correlated features, redundant features will not be considered, actually. Yeah, so there may be, so first of all, attribute independence, meaning that we may miss some features that are in combination together important, but have a low correlation to the class label on their own. Yeah, so they are irrelevant on their own, but together would be highly relevant. We will miss them because of the independence assumption, and also redundant features are not identified because we just measure how strong each feature is correlated separately to the class label, and we don't consider correlations among the selected features. Yeah? So we don't consider redundancy among the selected features. But that's how it is. Yeah. Anyway. Okay, so that was forward selection feature ranking, and next up will be backward elimination and random subset projection. So the other way around, so to say.